The bayous and swamps of Louisiana. Some of the most abundant mineral deposits known to man have been found beneath these marshy lands. In the 1860s, roughnecks and drillers from Texas were sent to Calcasieu Parish to look for oil. They found sulfur instead. Elemental sulfur had become a valuable and versatile mineral in the 1800s. The discovery of the process for making sulfuric acid led to the development of the phosphate fertilizer industry. At that time, the United States was heavily dependent on European suppliers of sulfur. Their deposits were mined by open pit methods. The deposits found in Louisiana were locked away under soft mud and shifting sands. Attempts to sink shafts into the soft terrain surrounding the sulfur met with no success. In the late 1800s, Dr. Hermann Frosch, a German-born scientist, devised a method of using oil drilling equipment to tap into sulfur deposits from the surface. The Frosch process succeeds due to two key properties of sulfur. Sulfur has a low melting point and is insoluble in water. In the Frosch process, holes are drilled and 3 concentric pipes are set into the deposit at different depths. By injecting the heated water into the sulfur-bearing formation, the sulfur is melted. It then forms a pool at the bottom of the well. The hydrostatic pressure of the water being injected into the well forces the liquefied sulfur several hundred feet upward into an inner pipe. Compressed air is then injected into the column of molten sulfur to help lift it to the surface. On Christmas Day in 1894, the Frosch process was proven a success when the first molten sulfur flowed out of a well into a wooden barrel at the Calcasieu mine in Louisiana. The basic process has changed very little since those early days, but it is unlikely Dr. Frosch would have imagined the scale of production his small commercial venture would lead to today. Over a half a century later, the same bayous and swamps that were the proving grounds for his method would play another important role in the history of sulfur mining. These backwaters and bayous would provide a pathway for colossal frameworks of fabricated steel. Steel that would be pieced together into one of the largest offshore sulfur and oil and gas developments ever undertaken. In 1989, a joint venture led by Freeport-McMoRan Incorporated and including IMC Fertilizer and Homestake Mining Company made the first domestic discovery of sulfur in 20 years. It proved to be one of the largest in the history of sulfur mining. The deposit also contained a significant oil and gas field. The main pass deposit was discovered in the Gulf of Mexico, 17 miles east of the mouth of the Mississippi River, in 210 feet of water. The reserve itself lay another 1,000 feet below the floor of the Gulf. Freeport-McMoRan's geologists utilized seismic exploration data from the area, as well as state-of-the-art computer analysis to define the deposit. Proven reserves of 67 million long tons of sulfur, 39 million barrels of recoverable oil, and 9 billion cubic feet of natural gas were found. After a feasibility study was completed in September of 1989, engineering, design, and construction were ready to begin. The design of the platforms incorporated many of the same concepts used at Freeport's offshore sulfur mines at Grand Isle and Caminada. However, the main pass mine would be a massive undertaking in comparison.
I think complexity, size-wise, magnitude, it's probably the most fantastic project in the Gulf of Mexico. The rates, in my mind, ahead of some of the deep water projects. They're the same amount of money, but not near the complexity and complication we've had in coordination of installing this project.
Freeport mined sulfur deposits at Grand Isle, Caminada, and Garden Island Bay for many years. But these world-class deposits can easily fit within the defined area of the Main Pass Reserve. During the summer months of 1990, the Main Pass mine began to take form. The complex itself would be composed of 6 main platforms, 9 bridge supports, 13 bridges, and 3 separate oil and gas platforms. When completed, the Main Pass mining complex would stretch to over 1 mile in length. The living quarters could accommodate up to 186 men and women during their week-long work shifts offshore. The power plant module would provide 17.5 megawatts of electrical power and produce 11 million gallons of heated water daily for use in the mining operation. 2 insulated tanks with a total capacity of 24,000 long tons would hold the molten sulfur for its shipment to onshore facilities. A minimum of 1,600 sulfur wells would be drilled from the 2 production platforms during the mine's active life. Once construction started, crews worked around the clock to meet the demanding work schedule. The weight of the steel used in building the main pass complex was equivalent to the weight of 80,000 medium-sized automobiles. To help this steel withstand corrosion during the mine's estimated 30-plus years of operations, 250,000 gallons of paint were applied. The combined deck area of the structures equaled nearly 7 acres. Although most of the fabrication took place in Louisiana, Mississippi, and Texas, manufacturers throughout the United States provided important components. In total, 1,153 companies from 33 states helped to complete the massive project. If the coordination of these activities weren't enough, the entire project was completed in the incredibly short time span of 28 months. Through long hours of planning, countless meetings, and round-the-clock construction schedule, one thing remained foremost in everyone's mind. They were participants in one of the greatest engineering and construction projects in modern times. The jackets supporting the main deck sections, such as the power plant and production platforms, consisted of 8 legs. The smaller bridge support jackets would carry less weight and consisted of 4 legs. The sides of each jacket were laid out and constructed on the ground. These sides were then rolled up or uprighted and attached to one another to form a completed jacket assembly. These roll-ups were accomplished using up to 6 cranes working in tandem. Each completed jacket stood as tall as a 28-story building. Men, women, and machines labored during the blistering summer months of 1990. By the end of September, the first 8-leg jacket was completed and ready for transporting to the mine site. A send-off ceremony was held to commemorate the event. This was a chance to reflect on the significance of the undertaking. The ceremony would provide only a brief pause in the construction schedule. Many months of intense effort lay ahead for the engineers and construction personnel. Once fabricated, jackets and deck sections were loaded out and secured onto the top of transport barges which were towed to their final destination in the Gulf of Mexico. One by one, these jackets and their corresponding deck sections left the fabrication yards, traveling down the meandering bayous and bays on their journey to the site of the main pass mine. When these components reached their destination offshore, they were lifted into place by huge derrick barges. Heavier jackets required launching from the transport barges before being uprighted. The derrick barges used during the offshore construction had lifting capacities of up to 4,400 tons each. Derrick barges were anchored in place using a state-of-the-art global positioning satellite system. Once the derrick barges were in position, the jackets were upended to within 1.5 feet of their design location. Pilings were driven through the jacket legs to permanently anchor the structure to the floor of the Gulf. Deck sections for the bridge supports and main platforms were then installed. The massive bridges, which were also constructed in Gulf Coast fabrication yards, made their way offshore to complete the connection between the jackets and deck sections. The deck sections and connecting bridges would set at a height of up to 100 feet above the water's surface. This would provide adequate protection from storm waves in the Gulf of Mexico. The bridges, whose lengths varied from 236 to 600 feet, were lifted into place by the massive derrick barges. These connecting bridges would slide on Teflon pads to compensate for shifts in the mining structure's height as the underlying ore deposit was depleted. The process of setting jackets, decks, and bridges was repeated throughout the fall and winter of 1990 and the entire year of 1991. the elements had a major impact on the construction schedule. Days and weeks were sometimes spent waiting for foul weather and high seas to calm. Construction onshore was also hampered by record rainfalls of over 100 inches in 1991. During construction activities offshore, mining was already beginning on parts of the complex that were in place. Temporary living quarters were stacked onto the bridges and drilling operations were begun. The mining of the main pass reserves placed unique demands on the engineers who designed the mine structures.
There have been many unique challenges faced on this project. From the structural engineering standpoint, the most significant has been for designing for subsidence. As sulfur is mined, the entire area around this complex is going to subside, from the quarters building behind us to the drilling rigs at the center of the complex. That causes unusual strains in the soils which affect the piling for the platforms. That has caused some very thick piling required, including 100 KSI material, thicknesses up to 5 inch for a 60-inch pile. And the technology required to solve that problem took the talents of McDermott Ake and Fugro McClelland over a couple of years to develop.
One of the most demanding jobs of the offshore construction phase was the power plant module lift. It was the largest single lift ever accomplished in the Western Hemisphere. At dawn, December 6, 1991, 5,450 tons of steel and equipment were gently lifted 100 feet into the air by 2 derrick barges lashed side by side. Its placement onto its lower deck section took less than 3 hours. The power plant module is the life force of the mining operation. It provides the hot water used in the frosh mining process and provides the electrical power for the entire mining complex. The 4 boilers in the power plant module will produce 11 million gallons of water per day, superheated to 325 degrees Fahrenheit. This superheated water is a key element in the mining of sulfur deposits in salt domes. Sulfur and oil and gas deposits along the Gulf Coast are sometimes associated with the occurrence of these salt domes. These massive geologic structures are the evaporated remains of prehistoric inland seas. Over thousands of years, sediments from river systems were deposited over these evaporite basins. These sediments were rich in hydrocarbons. The weight of the overlying sediments created internal pressures in the salt, which caused it to form domes which rose to within a few hundred feet of the Earth's surface. Elemental sulfur was formed in the caprock of salt domes during a complex sequence of events. Naturally occurring anaerobic bacteria fed on anhydrite and hydrocarbons to form H2S gas. The gas was transformed into elemental sulfur, which remained trapped within the limestone caprock of the salt dome. Less than 1% of the salt domes occurring in the Gulf of Mexico basin have commercial quantities of sulfur associated with them. In October of 1991, with construction proceeding on the sulfur mine, the first gas production took place at Main Pass. Oil production began 1 month later. The Main Pass mine development represents the first time oil, natural gas, and sulfur has been produced in significant quantities from the same geologic formation. This unique co-development has resulted in a number of operational synergies. During the injection of heated water into the sulfur formation, the oil is warmed, becoming less viscous, which increases the recovery rate. The sour gas flows to an amine Claus processing unit at the facility platform. This unit is designed to remove the hydrogen sulfide, or H2S. The product of this removal process is elemental sulfur. It is the first time such a unit has been used offshore in the Gulf of Mexico. The gas sweetened by the amine unit is then used to enhance the quality of the oil being sent by pipeline and barges to refineries. A portion of the processed natural gas is sent by pipeline to the power plant of the sulfur mine to be used as fuel for its boilers. The converted sulfur extracted from the sour gas is sent to the storage and handling facility of the sulfur mine by a separate pipeline. Offshore construction activities on the Main Pass project were completed in early January of 1992. Several months of hookup and testing were required before the first hot water could be injected into the sulfur wells. The water used in the mining process is a mixture of seawater and brine obtained from wells located deep within the salt dome. The heating of salt water with all its corrosive properties was a challenge met by the engineers of previous Freeport sulfur mining operations. It requires the use of unique construction materials and proprietary water treatment technology. Along with the fabrication of the sulfur and oil and gas platforms, 2 new sulfur-carrying vessels were under construction in shipyards along the coast of the Gulf of Mexico. The double-hull vessels measure over 400 feet in length and 75 feet in breadth. Each vessel has an insulated tank with a capacity of 7,500 long tons of sulfur. The vessels will make round trips from the mining complex to the Louisiana coast with their cargo of molten sulfur. From a terminal in Port Sulphur, the molten ore will make its way to chemical manufacturing facilities throughout the United States and other parts of the world. In addition to the offshore mine, an inshore base was constructed in Venice, Louisiana. This base serves as a logistics point for moving men and materials to the offshore mine. When completed, the total cost for the construction of the Main Pass mining complex was $880 million. With oil and gas production well underway, the sulfur production personnel were anxious to prove their mettle. On April 28, 1992, the first flow of this much sought-after mineral reached the surface. It was a moment not unlike the one experienced by Dr. Frosch and his men so many years before. As with their predecessors, the people of the Main Pass project stood at a crossroad. Behind them lay years of planning, innovative engineering, and intensive labor. Ahead lay years of continued effort to mine the rich mineral resource. For the duration of its active lifespan, Main Pass sulfur will be a basic ingredient in the production of fertilizers for America's farm belt, helping to grow the corn, wheat, and other crops that nourish us daily. Nearly 2/3 of the sulfur produced worldwide today is used in the process of making phosphate fertilizers. Other products produced from sulfur will touch our lives in ways we would little imagine. The paint for our homes, pharmaceuticals, the tires we ride on to work and play. Sulfur is an important building block in the chemical processes that create the variety of products we use daily. The pioneering spirit of those early drillers in Calcasieu Parish and the pioneering spirit of those who helped engineer and build Main Pass Mine should not go unnoticed. It is because of their efforts that we will have a continued supply of this important resource for the future.